pointer uh, from cursor to laser.
Yes.
From
Well, it's okay. I don't mind.
if you want, then you can.
I'm afraid, that it will not work any longer. And how does it work now? No, no. Yeah. Yeah, but it's okay. It's okay. Sufficient. With my hands.
It will make a delay.
With my hand. No, it's okay. Okay, welcome, Mia.
Yeah,
Oh,
we'll just
please.
start. So, good afternoon and welcome to all of you. It's very nice to see a lot of young faces in the audience attending this talk. So, this talk is pitched at a popular level for the undergraduates and the master's students. The title of the talk is From the Camera Obscura to Large Optical and Radio Interferometers by Professor Jean Surdej, who's visiting us nowadays at Aries from the University of Liège in Belgium. So we'll just begin with a brief introduction about Jean.
Very brief.
He has followed a career under the Belgian National Fund for Scientific Research, where he became a research director in the year 1995, and at the Liège University, where he became a full professor in the year 2007. He has also been a staff astronomer at the European Southern Observatory in Chile, in Switzerland and in Germany, and at the Space Telescope Science Institute in Baltimore, the United States of America, just after the Hubble telescope had been repaired. So he has been an integral part of all of these organizations. He is also a visiting professor at the University Adam Mickiewicz, Poznan, Poland, and a Vajra adjunct faculty at Aries Nainital. Since October 2017, he's also involved in a lot of research activities, teaching and formation activities abroad in countries like Qatar, India, Chile, and Poland. His main astrophysical fields of interest are radiative transfer in expanding atmospheres, asteroids, quasars, gravitational lensing, telescopes, and optical interferometers. So please enjoy the talk and feel free to interact and ask questions that you may have. So welcome, Jean. Thank you.
Thank you very much. Thank you very much, Natalia. So I don't know, it works? Yeah. Yeah. Yeah, so it's my pleasure to be here, and where the main motivation for us to be here, is of course to participate to the ILMT project. And I encourage you, after the seminar, to look at the scale model of the ILMT, so of the International Liquid Mirror Telescope, which is just outside this big room, where there is a demo, So I think it's very, very nice if you, after the seminar, can spend some time, and look how it works, because it's a lot of fun. So in the talk of today, there will be some redundancy with the talk I presented 2 days ago, or yesterday, in fact, it was yesterday. And but to go to optical and radio interferometers, I need to start first with the camera obscura again, and address also the problem, of the convolution that we mentioned yesterday. Good news, it doesn't work. Okay, camera obscura, pinhole camera. So this is a very nice activity for public outreach, to use a poster tube, On one hand, you put a aluminum foil with a small hole, and then on the other end, some butter paper. And with that instrument, you may look at the sun, for instance, Well, classical way to construct one, is just to make use of this blueprint, and to make the construction, of course. And you see on the left side, there is a little hole. And on the right side, where you see a dark rectangle, you would put the butter paper. Now, as you know, most of you know, well, if you look at the light of a candle, the top part of the flame will be imaged on the bottom part of the butter paper, on the rear side of the pinhole camera. So it will be an inverted image. Now, what I propose to do, is that you use, but especially the poster tube, to look at the sun. So you see here the sun, Then it's very good to know, yeah, what is the value of the angular diameter of the sun? In fact, if you like, well, you know the value in degree, alpha degree, about 30 arc minutes, yeah? But most interesting is to know the size, angular size of the sun in radian. And to do that, yeah, if you use your sun, which size is about 1 centimeter, and put it at a distance of 114 centimeter from your eye, you may start, well, you may finish ending occulting the solar disk. If you put it too close, of course, you will hide the solar disk. But just at 114 centimeter, if you go farther, then you will see the sun. Yeah? Which means that the angular size is 1 divided by 114. This is the tangent of the angle, but the angle is so small that you may assimilate it here at its value expressed in radian. Now, let's assume that the length of the poster tube is 114 centimeter. What would be the linear size of the solar disk seen on the butter paper? So I'm asking the students from Nainital who came today to give me an answer. What would be the linear size? Well, if not, we pass to the students, PhD students, what would be the linear size? 1 centimeter, yeah? Of course, because the angle here is exactly the same as the angle here. And if here you have 114 centimeter, it's like the length of my arm, yeah? This will be the linear size of the sun, yeah? 1 centimeter. Of course, the sun is seen upside down, as for the candle. Now, as you know, in the foliage of the trees, there are many holes, yeah, between the leaves, especially when it is windy, yeah. The holes are getting formed, disappear, they appear. And it's no surprise that on the floor, on the ground, you may see many images, yeah, of the solar disk. Now, of course, the angle under which these are formed is also 1 divided by 114, yeah. So 114, yeah, is a very nice number to remember. Now, if I assume that the linear size of solar disk on the ground is 5 centimeter, yeah, you may determine, yeah, what is the distance between the ground and the hole in the tree, yeah. So you just multiply 5 by 114, yeah. You find that it's about 5 meters 70, yeah. And this is very nice to tell, small children, that they may estimate the height of a tree by just looking the solar disk on the ground, measuring, their size, and then multiply by 114 or by 100 to transform centimeter in meters, yeah? And you find the height of a tree, yeah? This works very fine, yeah, very near to the tropics or in Kerala, where the sun gets very high, but also here in Nainital, in summertime, the sun gets very high in the sky. Okay, now formation of solar disk, and now I will come to the theorem of convolution. So you see, well, the solar disks are seen everywhere, well, on the ground. This is on the floor. Well, here you see it on a wall. And this is a small video showing, well, the first solar disk that we observed, in fact, in Provence Observatory. So it's in south of France. Well, on the table, we were amazed to see, many, many disks like that. And you see as the wind is blowing the foliage here, where the holes are forming, disappearing. And you see that always the semi-major axis of the solar disk is always the same. Now the semi-major axis can be longer because of the inclination of the sun, yeah? But here in India, the sun gets so high that it's almost a circle, yeah? So if you measure it, as I said, you multiply by 114, yeah? Well, you find out, yeah, in the tree where the hole is located, yeah? To see the hole in the tree, what you do, if there is a solar disk here, you try to put the shadow of your head on the solar disk, then you look and you see, yeah, the hole in the tree. And well, the hole is very well seen when you see the flash of light, yeah, because well, then the light from the sun, yeah, is passing, yeah. It's what you see here. Now, well, this, yeah, I try to see, yeah. This shows that the solar disk, of course, yeah, travel as a function of time. Yeah. We see them moving here, yeah, on the wall, of course, yeah. And it's very interesting to find out, yeah, what kind of path, yeah, they follow, yeah. And for this, well, I make the following demonstration, yeah. When you look at the sun, yeah, well, the sun, yeah, makes a circle during the day and night around the northern star, yeah, which is very low here in Nainital, yeah, well, just above the ground at an altitude of about 30 degrees. Now, the light rays which come into your eye, yeah, you agree, see, sweeping a cone, the surface of a cone, yeah, you agree, because well, it goes from the circle to your eye. Now it enters your photographic camera or the optical instrument, yeah, and so the cone is intersected by a plane. And when you intersect, yeah, a cone of light with a plane, you get a conic, yeah. Now, if the plane is perpendicular, yeah, to the solar rays, you'll get a circle, yeah. But on the ground, usually you get a parabola, range of a parabola. It could be an ellipse. It depends at which latitude you are. So this is what I was saying, you know. This is, for instance, the circle showing the path of the sun during daytime. Now the light entering my optical system. And then it intersects the plane of your CCD camera in the shape of a range of hyperbola in this case. Now, this is also a very nice activity to do with young pupils, yeah, or students, to use a camera and during the daytime to make a time lapse of the motion of a shadow on the ground, yeah. Well, in this case, oh no, this is already the quiz, so let us activate. So this is a video which was made in December from our location in Belgium, yeah. And well, you see the shadow of the lamp shade here. Then well, there is a feature here too, a bit darker, yeah, which is a feature here on the pillar. And you've seen the trajectory, yeah. Now, does anyone have an idea? Yeah, it's in winter, yeah, so near 21st of December, what kind of trajectory it could be. But we are in the north, yeah, in Belgium, plus 52-degree latitude north. Yeah. Well, in fact, I will show you now with a rapid motion the shadow. Okay. Now, well, I've marked here with the red disk and blue disk, yeah, the two shadows of the features I mentioned, the lampshade and the feature on the pillar. This is the trajectory. You know, this is the real trajectory they follow. So these are branches of hyperbola. And in fact, on 21st of March or 21st of September, it's very different because the sun at that moment is at the equator, yeah? So it's perpendicular, yeah, to the south-north axis. And so, well, the sun makes a circle too, but in a plane. And so on that day, on the equinox day, yeah, the intersection of two planes is a straight line. This is, well, interesting to know that on that day, not only the day and night are equal in length, yeah, but all over the world, people are observing the path of the shadows as a straight line. Okay, now just to show you that you can, with your fingers, make small holes and project on a wall, yeah, solar disk. Now I come to the camera obscura, yeah. Let's assume that I'm using candle and I set the candle very far to the left, yeah, well, at the distance of the sun. So everybody agrees that through the first hole, I see an upside down image of the sun. But now through the second hole, I also see the same image, same for the third hole. But what is very important here to observe is that, well, on the butter paper, the separation between the two images is exactly the separation between the two holes, because the light rays come from very far away. Okay, now if you use a heart as a source of light, yeah, it goes, yeah, very far away. I project its images, and of course you see an upside down image, yeah, with translation exactly equal, yeah, to the separation between the holes. Now I will come to the theorem of convolution, yeah, and then, well, later on, yeah, we need some light on the blackboard, but to start, yeah, I do the following. Well, first I speak about surface brightness and blur of images. These are the holes illuminated here by the red heart. And so when you see, if you are very close, yeah, to the holes, well, the images here are mixed up, yeah, and there is a blurring of the images. As I go further away, well, I see more distinctly those hearts and still further away, yeah. So I may easily establish that if H is the size of the hole, yeah, well, the blur, yeah, is proportional to the H square because it is the size, yeah, to the two-dimensional size of the hole. But it's inversely proportional to the square of the distance because then the hearts are better separated from each other, yeah. So, okay, we see the relation, the blur is proportional to H divided by D square. But what about the surface brightness? Well, I know that surface brightness will depend on the size of the hole, so on the H square, yeah. But because of a geometric dilution of the light, yeah, due to the distance, it's inversely proportional to D. So when you see on the ground, yeah, a solar disk, yeah, fainter it is, yeah, fainter it is, more details you will see. And brighter it is, less details you will see. Now, yeah, I come to the theorem of convolution. So the hole is a heart illuminated by the sunlight. Now what I do next, well, I divide the heart in many infinitesimally small elements, surface elements. Well, in this case, I took 9 elements, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, well, I adopt the Cartesian system of coordinates, x, y, z, yeah? Then I choose a surface element, infinitesimally small, set at the position 0, 0, 0, yeah? And at a certain distance, I put a screen along the z-axis, so at a constant value of z, and I project the image of the sun. So what I see this image, of course, yeah, at position xy. So the intensity at position xy is just, yeah, the image of the solar disk produced by a hole infinitesimally small, multiplied, of course, by the size of the square, delta x0 times delta y0. Now, if I take another small source element, yeah, which is also square, and I combine the two, what will happen? Well, it's easy. As I said before, the solar image will just be translated, you know, by x0, y0, yeah, okay? So it will be a mixture of the two. And the summation of those two images will give me the intensity, well, of the first one, plus the second one, just translated, easy. Now, well, let's assume that we have n elements. So what I do, just make a summation, yeah, on x0 equal 1 to n, y0 equal 1 to n of the solar disk image, translated, multiplied by this, yeah. And now I take the limit, yeah, n going to infinity, yes. And what happens, of course, I see double integration, yeah, of h of x0, y0. What is this function, yeah? It is the holes. If I'm inside the hole, it's 1. If I'm outside the hole, it's 0. This is the solar disk translated, yeah, and double integration. So this is a convolution product, yeah. So could I get some light here just in front? Yeah. Because yesterday I think Ranchu, yeah, talked about, yeah, this convolution theorem, yeah. And so what you see is that I of xy equal to double integration of the whole function, yeah. So x0, y0, I solar disk and delete it. So x minus x0, y minus y0, dx0, y0. Then he said, well, this we can represent here as being equal to convolution of h by h. Then he also mentions that it's commutative. Yeah. Well, to demonstrate the commutativity, yeah, well, you could do the following. Create a, well, we make a change of variables. So x0 prime would be equal to x minus x0. Then y0 prime would be equal to y, sorry, minus y0. So you find that dx0 prime is equal to minus dx0. dy0 prime equal minus y0. Now we make this change of variable. And we obtain that it's equal to. Well, first I just write xv. X of minus x0 is x0 prime. Y minus y0, y0 prime. And h of x0, well, I find that x0 is equal to x minus x0 prime, y minus y0 prime. And then I have dx0 prime, dy0 prime. This is exactly the convolution product of SD by H. So I've demonstrated yes, the commutativity property. Well, yesterday, I think Pranchu had an image where it was a science image, yeah. It's a science image, it's Y. And then he had an image, it was a reference. Then he made use of a filter. Yeah. Then, well, F also XY. Then say, well, what we do, yeah? We try to find out where the filter expression, which is such that when you convolve ISC, so no, yeah, it's the same by the filter, you obtain IREF, yeah? So this is a convolution product. This is what he was showing yesterday, yeah? Something like that. Yeah? Okay. Now, so later, yeah, it's illustration of the convolution theorem. There is a quiz for it. I have a hole, which is circular. Now I take a heart, you saw, inverted heart, red color, which is at the distance of the sun and which is illuminating the hole. Now I will set a screen very close to the hole. And I would like to know which shape I will see. Shall I see a hole or a heart? Who is in favor of a heart? Who is in favor of a circle? Yes, but many are not in favor of a circle. It means they are in favor of a heart. So just raise your hand. Yeah. So who likes the hearts? Oh. No one? Okay, you say a circle. And if a circle, it will be red or blue? Red? Blue? Blue. Yeah, there are some blue. Yeah. Why not? The correct answer is a circle red. But now if I set the screen very far away, now, well, how can I see that property yeah, from all this expression? Yeah. Well, I would do the following. So this I don't need for the moment. Yeah. Well, if I'm very, very, very close, yeah, to the hole, the solar disk is a very small dimension. It's like a Dirac function. So here, I could just replace this by a Dirac function. Now I integrate that. I know that x0 would be equal to x in that function, so this will be equal to a of xy. So right, red this. Now, if we set, the screen very far away, what will it be? Will it be a disk or a heart? Who is in favor of a disk? Who is in favor of a heart? Yeah, you're romantic, huh? Which color? Red? Okay. Direct image or upside down? Hey, it's not upside down. Why it's not upside down? It's because the original image was upside down, yeah? Yeah. So everybody failed. So I'm the winner. So now this is a nice activity, yeah, to make at school too, or at any institution, yeah. You just use a cardboard and you perforate, with small holes, yeah. So you see on the top there is a elliptical shape, stellar shape, square shape, and circular shape, of different size. Well, at the bottom, yeah, they are all square with a very, very small size on the bottom right. And there's a second hole, yeah, you see at the top, is also very, very small, yeah. So I draw your attention on that. Then what you do, well, in our city, the sun, yeah, always remains very, very low. So if you put that on a window, it works perfectly, yeah. If I would be living in Kerala, yeah, I would set, yeah, the cardboard, yeah, horizontally with respect to the ground. So now we make use, yeah, of a A4 paper and see, put it close to the window. And then, well, we recover the real shapes of the holes. Just like for the case of it was a disk, red disk. Well, a bit farther away, well, you see the blurring, yeah? And when to calculate this image, yeah, you would just make use of the convolution theorem. Now, as we go farther away, now you see on the solar disk, yeah, well, a cloud. It's because at that time a cloud just passed, through in front of the sun, and you could see it on all the images, yeah. Could we switch off the light? I don't know where. Yeah, thank you. Yeah. Now, you see, if you set the screen still farther away, this is fun, yeah, that you see a solar disk, yeah, whatever is the shape of the hole, yeah. And this is the reason why when you see the solar disk on the ground, it does not really depend on which side, on which shape, yeah, of the holes in the foliage of the tree. And then you see that the second hole at the top, yeah, well, is a fainter one, but in principle shows the most detail. Here it's extremely faint. You don't see it here. Here is a zoom view. Okay, and now, and if the diameter of the pinhole, yeah, was getting down to 0, what would happen, yeah? We would get an image probably infinitely clear, but infinitely faint, yeah? But not quite. If the hole gets too small, well, we need to use the diffraction theory of light, yeah? Well, to calculate what happens, yeah? And in a moment, yeah, we brought, yeah, some screens, yeah, with a small pinholes, and we'll make an experiment. Now, well, this is a bit redundant, yeah, for those attending the workshop, IDMT workshop, but many participants are new. So I just show you how you go from camera obscura to the telescope. Okay, we start again with a candle. We know that we'll get a first image inverted. Now, well, we astronomer, what we would like, yeah, is really to stack the second image, not there, but on top of the first one to see it brighter, yeah? So how to do that? Well, just make use of a small prism, yeah, to deflect the light rays, yeah? So we would install here a small prism, and of course then, the light rays, yeah, would go superimpose over the first image. You do the same for the bottom hole. And then in the center where you just set, yeah, a prism with two parallel faces. Yeah? And what you see, what we have constructed a converging lens. Yeah, and this is what the objective, yeah, transparent objective or telescope is. Yeah. Now in this plane where normally we had some butter paper, we would call it the focal plane. Yeah. And here we would set a detector, or what you could use if you would have the butter paper, use a magnifier, an eyepiece, yeah, and look at the image, and you would see the image of the source, yeah, with some magnification. Okay. Now, unfortunately, yeah, well, when the light encounter, yeah, reflecting or transmitting surface, yeah, we have to make use of the wave theory, yeah, for light, yeah. So we adopt the Huygens-Fresnel principle, according to which, yeah, if you have a plane wave, you may consider it as composed of an infinite number of a small source of light, which all emits, yeah, secondary wavelets. After some time, well, you see where those wavelets would be, and if you take the envelope, yeah, of this, you would retrieve, yeah, still the plane wave. You could do the same for a spherical wave, yeah. Consider that there is a large number of secondary source emitting small wavelets, and you see that after a certain time, the envelope, yeah, would restitute the spherical wave. And then Fresnel added the fact that if two wavelets, yeah, interact between each other, they interfere. If they oscillate, yeah, in phase, then the signal would be improved, strengthened. If they oscillate in phase opposition, you would see no light. Yeah. And well, you make use of the same principle when you want to know from a point-like source, yeah, emitting a beam of a parallel light rays, which are converging in the focal plane of a telescope, what kind of image you would get, yeah? And well, the image is known as a hairy disk, yeah? It has an angular size, which is in radian 2.44 times the wavelength at which you make the observation divided by the diameter of the aperture, yeah? Now, if you make use of a telescope, which size is about 15 centimeter in diameter, well, the hairy disk could have a width of about 1 second of arc, yeah? What we'll do now, well, 1 second of arc, the eye cannot see that, yeah? Because our angular resolution is about 30 seconds of arc, yeah? But if you would take a hole of 1 millimeter, yeah, in diameter, this is 150 times smaller, yeah, than a dish of 15 centimeter, yeah? Which means that instead of having 1 second of arc, we would have an hairy disk with a width, a diameter of 150 second of arc. In that, our eye could see. Now we brought, yes, some small screens drilled with a single hole. And well, you will have the opportunity, yeah, to look through it. I don't know how many we are, yeah? We brought, I think, 64 little screens. So we will see if we are more or not. So this is the first experiment. So it's just a screen like that. Now there are two pieces of aluminum. Well, on one side, you see just one dot, it means there is a single hole. So we'll first make use of the single hole screen. We will be looking at it, yeah? And later on, but not now, we'll be looking at the two holes. And then you need some explanation to know what happened, yeah? So it was on Friday, yeah, that Kuntal told me, well, colloquium, yeah, so what shall we do? So we didn't want to be too redundant, yeah, with the LMP project, yeah. And so with my wife and I, yeah, we spent several evenings, yeah, we're constructing these small screens. Well, I could ask maybe Tushar, how much time it took you to make one such a screen? A good one, what? 15 to 20 minutes, the last one, yeah? But the first one, how much? Yes, yes. So you see, you multiply by 64, yeah. So it's a demonstration that we were very well occupied, you know, each evening, yeah. So okay, well, we may start distributing the screens, yeah. So Pranchu, Naveen, Kuntal, Sarah, Anna, Tushar. Yes. Now, I have some here, please. 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 And please. I have no more. Yeah. Now, what I will need, yeah, some sources of light, right? And the best point light source we could have, you know, is a light from a cell phone. Personally, I don't have cell phone, and I feel very well. Yeah. Yeah, and I think the best use you can make with a cell phone, yeah, is to provide me with a source of light. Yeah. So could I get some? Yeah. So we will just install them here, maybe on the table. So where's a cell phone that I could use? Yeah, very good. So Gokul, very good. Here I have already the second one. Yes. Yeah, we'll just put one here. Then maybe second one there. Yes. Now, third one, maybe here. On this. Yeah. Yeah, like that. Yeah, very good. Everybody will see. Yeah. So we have 3 cell phones. Yeah. Yeah. Now, yeah, you well just take the single hole screen. Yeah. And look, and you should see the airy disk. Yeah. So it means maximum concentration of light in the center, surrounded, yeah, by a dark ring, first dark ring. Most of you will see the first dark ring, but not the second one, not the third one. It's because when you make such a hole, it must be extremely small and circular, and it's quasi impossible to make that. Yeah, yeah. So does everybody see the hairy disk? Yes. And do we have a sufficient number of screens, or we are missing some? If not, you may share, you know. Ça va qui tue déjà avec 3 lampes, ça suffit. Hein? Comment? Oh yes, a picture, yeah, correct. Yes. So you see the diameter, yeah, of the dark ring, yeah, is a 2.44 lambda over d, probably something like 1/52 of arc, yeah, because the diameter of the hole is about 1 millimeter, yeah. Okay, so now we will continue, yeah. So this is Sarvesh. Yeah. Oh no, Sarvesh is here. Yes. Oh, okay. You, je sais pas. And this one, to whom it belongs? Yours, Gokul? Yeah. Now we may switch off. Yep. Because we must continue. Yep. Well, there will be a second experiment, yeah, and then it will last a bit longer. So, well, I think it's very nice, yeah, to see yeah, the airy disk, yeah, made through a small aperture. So at home, if you want to repeat the experiment, just take a foil of aluminum, yeah, a small needle, and try to make a very, very tiny hole, yeah, well, perpendicularly. If you make it a little bit oblique, yeah, then it will be something which doesn't look like a circular hole, yeah. So you need some patience. Okay, so as I said, yeah, when you're looking at a star, yeah, well, I would say even at all the stars, yeah, and if there would be no atmosphere, yeah, especially from space, what you would see, yeah, for a star, whether it's a big star or a small one, whether it's red or blue, whether it's made of different compositions, yeah, you would always observe the airy disk and nothing else. If it's clear, well, near to us or very far away. So it's kind of disappointing, but the angular size would always be 2.44 lambda over d expressed in radian. Well, in the case of the 4-meter ILMT, yeah, 4-meter, the airy disk, yeah, is a diameter of 0.07 second of arc, so 7/100th of an arc second. Yeah? And it was seen in laboratory. Yeah? Now, well, if you increase the size of the telescope, well, you see the angular width of the central core, yeah, decreases. And now, well, if you look, yeah, with a medium-sized telescope, a distant planet, what you would see, it's a blur image, yeah, as you see here. Now, if the diameter of the telescope is larger, you would see, well, a more clear image, yeah, of the planet, especially from space, yeah. And this is why, yeah, many people, yeah, want always bigger and bigger telescopes. Now, in fact, what it's very easy to understand now is that the blurred image that you see of a planet through a telescope is nothing else than the convolution product, yeah? So the convolution product of the point spread function of the airy disk by the image of the planet that you're looking at with infinitely great details. Yeah. So you see convolution product came yesterday, today for the solar disk, and here again, yeah, for the image of an extended object given by the telescope. Okay, now, well, it's very nice, yeah, to use a telescope working by reflection. And if you would use a flat mirror, yeah, well, the light rays would go from the distant star back to the star, yeah. Astronomers don't want that. They want to focus the light rays, yeah. So it's easy to understand that you would like to curve the mirror, yeah. And it's the perfect shape, yeah, for a mirror to reflect into a single point, yeah. A beam of a parallel light rays, yeah, is the shape of a paraboloid. Now, well, this was the topics of the identity workshop we organized here during this week. It was to study the case of a liquid mirror telescope, because when you set a liquid, yeah, in a cylindric recipient in rotation around its vertical axis, yeah, you get naturally a paraboloid. So the liquid is reflective, like mercury. Well, it can be used as a telescope. Now, the focal length of the telescope, you see, is given by the gravity, local gravity, taking into account, yeah, well, the mass of the Earth, but also the centrifugal acceleration, divided by twice the square of the angular velocity. So, as shown here, you may decide, yeah, on which focal length you want to have, yeah. If the focal length is very work or not good, yeah. If the focal length, so you see the recipient starts spinning faster and faster and faster, then the focal length decrease. So you may decide on which focal length you want to give your telescope to make observations. Yeah. So in our case, the focal length is about 8 meters. And when you see here the telescope, yeah, just rotating. And there will be a visit, yeah, by the students attending the IMT workshop in 2 days, yeah, in Devastal. They will see this live, yeah. Now, well, yeah, I would like just to say a few words about Devastal. Devastal is a very nice site, yeah, where nature, yeah, is splendid, where the hills, yeah, where the far distant Himalaya, but not only, where you may also see rainbows, yeah, when you have rain. Well, sometimes when you get very nice thunderstorms, yeah, you see here, well, it's fabulous. The sound, the violence, yeah. But also sometimes it has been snowing, yeah. And this was at the time in December 2019, when we were forced to evacuate the observatory. Yeah? So we were told that we would walk with our luggages during about 2 kilometers. And finally, we walked 15 kilometers with the luggages, yeah? Because no car could come. Well, you see also during the night. Yeah, strange. Okay, so here, you know, fire, yeah, in the forest, yeah, very unfortunately. Probably it's not accidental, yeah, because well, some people would like to get more land. Now we have nice visitors, yeah. So be careful if you carry fruits on Thursday. Yeah, they are very curious. Well, this is a black francolin, yeah, kind of birds you see there. This is a crested hawk eagle, very nice. Then this I already showed before, yeah, it's a birded vulture. So there are vultures coming approximately every noon with the bones, yeah, and they are breaking the bones, yeah, on a rocky area just close to our telescope, so we see them. And after they are eating the bone marrow, yeah, which is inside. But we also like, yeah, observing butterflies, yeah. So these are painted ladies, yeah. Amazing, yeah. Then these are Indian tortoise shell, red admiral, and brown meadow. But there are also lizard, scorpion, leopards, yeah. And here, well, we had a big pleasure during our stay recently in Devastan, yeah, well, to listen to the birds singing, yeah. And well, my wife Ada found a very nice application for cell phone, which is free, called BirdNet, and it allows you, yeah, to just a moment to record, yeah. Okay, come here. I don't know. It you okay? It doesn't work, doesn't it? But it allows you to record, yeah, the sound of the birds. Then you may record it, you may analyze it, and find the name of the bird, yeah. And in this case, the pictures that you see here is the photographs that we could directly take, yeah. So there are many nice birds there. Now, well, about angular diameter of stars, yeah. Well, measuring the angular diameter of stars is just like measuring, you know, well, the size of the filament of a bulb, of a light bulb, you know, which is set at a very long distance, yeah. So you need special instrument. Why is it interesting to measure angular diameter, yeah? Well, it's shown here very rapidly, yeah. So this is a very far away star, which linear well, diameter is twice the radius, yeah, of course, yeah. And angular size is twice the angular radius, yeah. Now the angular radius rho is defined as a linear radius divided by the distance, yeah, which is a tangent, but so small that you simulate it, yeah, to the angle in radian, yeah. Now what we know is that the absolute flux of the star is the apparent flux of the star that you can measure, well, in an observatory, divided by the square of the angular radius. Yeah? What we would like to know. Now the effective temperature, yeah, this is the Stefan Boltzmann law, yeah, is such that the power 1 divided by 4 of the absolute flux of the star divided by the Stefan Boltzmann constant, yeah, would be equal to, you replace F by this expression, F divided by that. So you see that if you may measure the apparent flux of a star in an observatory and measure its angular radius, you may directly know what is the effective temperature, yeah? You can do that to apply to the sun. Measure the flux of the sun. Now you measure the angular diameter, you know, 1 divided by 114, yeah? You set it in that relation, and you find about 6,000 degree Kelvin, yeah? So very nice application. Now, how to do that, yeah? Well, first person who reported, yeah, the measure of an angular diameter is Galileo. he used a wire. You see here a wire like pendulum, and then he looked at Sirius, and he tried to, well, when he was very very near to the wire, he didn't see Sirius, but he went far away, and when he started to see Sirius, yeah, he said, well, this is its angular diameter, yeah, and he found that the angular diameter of a star is about 5 seconds of arc, which was already much better than what was thought before, because people thought that the angular diameter of the star was about 2 arc minutes, which is our angular resolution of the eye. Yeah, so it was already a big improvement. Do you have any idea why he found 5 seconds of arc? In fact, what he was measuring the seeing, yeah, the atmospheric seeing, the atmospheric turbulence. Yeah. Now, a second approach, yeah, to measure the angular diameter of a star is Newton. And well, you know, Newton is really very rational. He said, well, at what distance should I set the sun so that it would look like, well, Vega, yeah, the bright star in the sky, yeah? And he said, well, I know that the sun has a magnitude of about minus 26.7. This is what we know today, yeah? And I would like it to be a star of 0 magnitude. So 26.7 magnitude difference, yeah? So he said, well, the sun now, I see it under an angular size of half a degree at a distance of 1 astronomical unit. I want it to be faint like Vega, so he derived the ratio of the distances, yeah? And he found, yeah, that if it was at a distance of 7.7 parsec, it would look like Vega, and its angular diameter would be about 2 milliarcs again, yeah? So he was the first scientist really to get a very good estimate of what the angular size of the star should be. But of course, he did not observe it, yeah? And then comes Fizeau and Stefan, who proposed, you see, already 1870, that if you use 2 independent telescopes, yeah, and combine their light, let the light interfere in a single point in a coherent way, it means that the distance of the 2 light rays coming to the 2 telescopes and arriving from the star at a single point should not be different by more than a few times the wavelength of the light. Yeah? Then, well, you could estimate where the angular size of a star as if you are using a telescope which diameter is the baseline, the separation between the 2 independent telescopes. Yeah? So very nice finding. And you will understand in a moment why. If you do that experiment, what you will see the airy disk, and you have now, yeah, a 2-hole interferometer with you. So, but you need a font like source, yeah, in a moment. And you will see that the airy disk, yeah, is separated by fringes, yeah. Now, as you will rotate, yeah, your interferometer, you will see the fringes turning because they are always perpendicular, yeah, to the direction between the 2 holes or the 2 aperture, yeah. So now I need again, yeah, the sources of light. Yes. Non, toi tu fais la photo. Ouais. Ah, mais ça va bien, déjà 2. So is it okay like that? Yeah. Now maybe one more here. Yes. Yes, I can get yours too. Thanks a lot. Very kind. Yes. So do you see the fringes? Yeah. Do you see the rotation as you're rotating the screen? Yes. And you see, so the separation, yeah, between the fringes, yeah, is about lambda wavelength divided by the separation between the two holes, which is about 1.5 millimeter. So you see probably 3 or 4 fringes, or maybe even more. Well, closer will be the holes, yeah, and smaller they will be, more fringes you will see. Oh no, you will see less fringes, more separate. Yeah. Okay. So, well, the first, scientists, having discovered this phenomenon is Peter Young. Yeah. The experiment of Peter Young, yeah, with a 2-hole screen, yeah. And it's a very, very, very nice experiment, yeah. Okay, so I will just continue and restitute to the owners the phones. But I don't remember. Is yours one of these? Oh, yes, please. So here is the second one. Yours, yeah. Celui-là. Okay, fine. Okay, now here also, yeah, if you have a small telescope, you see a blurred image of an extended planet. Bigger is the telescope, better it is, yeah, and this is the aim of astronomers of constructing, the TMT, yeah, and also EELP. But if you use, yeah, interferometer, yeah, wow, you have a large gain in resolution. Now, this is a physical experiment, yeah. So this is something you could do if you have a small telescope or a small lens, Even a magnifier, yeah, would work. You see, there is a screen with 2 holes, yeah. And what we have seen is that if we just make use of 1 hole, we would get here a iridescent, yeah. See, no fringes, yeah. And now, if I would hide the second hole, what would you get here? Also, the iridescent, exactly the same, yeah, in the same position, because this lens, yeah, is our eye. It's exactly what we did now. But if you let the light enter the 2 holes, well, then you see the fringes, yeah. And now it's easy to understand why it allows you to resolve, angular or measure angular diameter of star. Let's assume that you have 2 stars, yeah, well separated into the sky, and you look at them, with an interferometer, so two single telescopes, where you see them very well separated. Let's assume they are very near to each other, so the fringes of one will cover the fringes of the second one, and still the visibility of the fringes will be the same. But look, if one of the 2 stars moves a little bit and comes in the minima of the first one, then you will see no fringes anymore, yeah? And to which angular separation this will correspond? Well, exactly half the separation between 2 fringes. So lambda over 2b. So you see, if the baseline is very long, wow, you may measure the separation between 2 very nearby stars, yeah? But you can do much, much more with interferometry, yeah? Looking at any kind of objects and characterizing, the sources of it with a fantastic angular resolution. Okay, this was the second experiment. Now, well, historically speaking, Fizeau in 1868, yeah, set a screen in front of a big telescope, yeah, with a baseline of about, I think it was something like 75 centimeters, the separation between the 2 slits, yeah. And he looked at all the bright stars of the sky, and he hoped, yeah, to see, well, the visibility of the fringes getting 0, yeah. So this is maximum visibility. This is visibility 0. He looked at all the stars and could not see any disappearance of the fringes, yeah. So he concluded that the angular radius of all the stars was smaller than 0.16 Fibonacci, yeah. Well, this is a view of the telescope in Marseille that he used, so 80 centimeter telescope. It's in a museum now. And then when Michelson, yeah, used a small telescope, yeah, well, less than 50 centimeter, and looked at the satellites of Jupiter. And he knew that the satellites of Jupiter had an angular size of about 1/2 of arc, yeah. And he could make the experiment, you know, with holes over small mirror and see the disappearance of the fringes. So he was the first to demonstrate, yeah, that this principle is workable. Then they made use, yeah, you see, of a big beam on top of the 2.5 meter Wilson telescope, in Mount Wilson, yeah. And they measured, yes, the first angular diameter of a star, which was Betelgeuse, yeah, red supergiant, yeah. So they knew that it was a red supergiant. Eddington informed him, yeah. Then, and the angular diameter they measured was 0.047 second of arc, so 47 milli-arcs again. So this is the biggest stellar diameter that has ever been measured. Now, Antoine Labeyrie in France was the first to demonstrate the feasibility of the principle using two independent telescopes. Yeah. Now, the difficulty is the following. Yeah. So you're observing a star with a two telescope. Yeah. And you must make sure that the length of the path of the light rays coming from the star and reaching, well, I would say the focal point here does not differ by more than a few wavelengths. Yeah. But the star is moving in the sky, yeah, which means that when the telescopes are looking, you know, vertically, where the path difference is 0, but everywhere else is non-zero. So you have to compensate for it, yeah. And therefore, you are using what is known as optical delay lines. So these are carriage on rails, yeah, which are constantly moving with a very high speed. First fringes that he saw from Vega, star Vega, because it was the brightest one. After he constructed, yeah, the large interferometer with two telescopes measuring 1.5 meter, and he had several papers published in Nature, yeah, resolving diameter of stars, but he was the first. And then, well, European astronomers, yeah, decided to construct, well, a gigantic, yeah, interferometer with a 4-8 meter, yeah, big telescopes, but not only, they added, yeah, 4 small telescopes, yeah, that can be transported very easily, yeah, from night to night at different places, yeah. Because, well, if you have 2 telescopes, yeah, separated along that baseline, you may recover good angular resolution in that direction, but not in that one. Yeah? So the idea is once to move the 2 telescopes like that, or then put them larger, well, farther away, well, to cover what is known as the UV plane, yeah? Which is a space frequencies plane. Well, here we have a few views of the VLTI at ISO in Chile. So it's fabulous. And when the ELT, yeah, is being constructed, yeah, on the other hill, yeah, that, but we don't see construction now. Well, these telescopes were also made by the Amos company, which constructed, yeah, the 4-meter ILMT. Now you see, these are the 4 big telescopes, and then here all the positions where can be set the small telescopes. Yeah, so you get many different baselines with different orientations. And then what happens in addition is that the Earth is turning. Yeah, so what the star sees, well, she sees the baseline changing in orientation and also in separation, because it's a projection, tangential projection on the plane of the sky. And so you are taking many data, and from this you may reconstruct, you know, well, the shape of the source of light that you're observing. Well, here is a more detailed, yeah, representation of the optical systems, and you see how many mirrors you need, yeah, to transport the beams, yeah, in the interferometric laboratory, such that the difference in length between the 2 beams does not differ by more than 5 wavelengths. Well, here you see the delay lines, yeah, with the carriage, and there are mirrors, and they are moving constantly during the nights from one end to the other. Same applies at radio wavelengths, yeah, exactly the same principles, but there you are collecting electromagnetic waves, yeah, and you may record them, yeah, well, on recorders a long time ago, yeah, well, now you record them on disk, yeah, and after you may interfere, well, the different signals together and do exactly the same way. So this is a VLA, very large array, SOCORO. This is the VLBA. So exactly the same telescope as the VLA, but covering the all United States, yeah? So you see from Hawaii on the left, yeah, there to Puerto Rico. Yeah? So huge baselines. And then when you are getting images with a very high angular resolution, well, better than the milliarcs again, yeah? And well, the reason is that you may get better angular resolutions is that it's easier to make interferometry at radio than at optical wavelengths, because the radio wavelengths are much larger, so the tolerances, yeah, are easier to fulfill. Here, GMRT, yeah, fabulous, yeah. So the work of Professor Govind Swarup, yeah, and his team, of course. Here, ALMA in Chile, it's a submillimetric array, where there you have about 60 independent telescopes, which are on a very high plateau at an altitude of 4,300 meters, yeah, so very high. You see this antenna here can be moved, yeah, on a very big transporters, equipped with many wheels. You see here an aerial view of the ALMA project. Now, just for the story, this was well, interesting to know. At the very beginning of the IDMT project, yeah, we were invited by Chilean astronomer to prospect a site there at an altitude of 5,500 meters. Yeah, so we went there, and we had like some hallucinations. Yeah, it was like if we would have taken some drugs. Yeah, because well, lack of air. Yeah, lack of oxygen. Yeah, but very good that we didn't go there, because well, it was crazy to even go. Yeah, so you see still the ALMA with a transporter, yeah, at work. Anyways, are getting, of course, fabulous images, yeah, of exoplanets and many other things. So here you see a photograph, yeah, taken in the direction of the South Pole that you cannot see from Magnetar. Now, well, just a small movie. This was taken in December, yeah. And you see Orion, yeah, here, going from right to left in that sense. Well, you may guess probably where is the northern star. You see it is over there. Do you see some colors here? Yes, okay. Yeah. Now I show you the same during the spring in Devastal. Oops. Yeah. And now look at Orion. Well, it goes in the opposite direction. What's the reason? Please. Did the rotation of the Earth change in between? No, it's from the same place, from Devastal, yeah? From Devastal, yeah? So it really depends on which orientation you set your camera, yeah? You see? Yeah. Yeah. Okay, now we see where's the Scorpion, where is there? You see Antares, the head of the Scorpion, the galactic center here. So you see a very nice view of the sky, yeah, from Devastal. It's fabulous. So with your iPhone, yeah, cell phone, you can make, I think, a very nice time lapse. here, what I would like to show you, well, we were about 1 week ago in Kerala, and then we like to take an image of the sunset, and then another one from Kanpur. And what you see is that, of course, the direction of the sunset is not the same, yeah, in Trivandrum as it is in Kanpur, as it would be here in Nainital. We try to make a time lapse, but the clouds came at the last moment, so we don't have yet. But the reason why I show it to you, yeah, is that, well, if you would be kidnapped, yeah, and put into a cavern, yeah, and you could only see, yeah, the sun setting down or star setting down, yeah, well, just remember that the angle made between the horizon, the direction, yeah, of the star or the sun, yeah, is 90 degrees minus the latitude. Yeah. If the sun goes in that direction, you're in the northern hemisphere. If the sun goes in that direction, you're in the southern hemisphere. Yeah? So by just measuring the angle, you will know in your cavern where you are more or less. Yeah? But you will never know what is the longitude. And this is the end of my talk. Yeah. Thank you very much. So this is well, an exoplanet detected with ALMA, yeah, in the submillimeter regime. So you see here circumstellar disk, yeah, from which planets they are being formed.
Thank you, Jean, for this very exciting and fascinating talk. I'm sure you've enjoyed this talk. So the floor is open for questions now. Please feel free to ask questions. So everything was very clear, I guess.
Yes, I knew that he would ask a question. Yeah.
Just small doubts, like this interferometric technique can be used in any wavelengths, right?
Yep.
The technique is the same.
Yes. Yes.
I see.
Of course, recording, yeah, the electromagnetic waves is different. Yeah. Well, in the optical, yeah, you need to let the beams interfere together.
Mhm.
Well, for instance, if you use the radio interferometry, yeah, at the very beginning, yeah, VLBI, yeah, they would record, yeah, the signals in magnetic tape, yeah,
Yeah.
with a very precise timing
Mhm.
incorporated, yeah. So you needed crystal oscillator, yeah, to be sure about the time. Then you take the tapes, yeah, and let the signals interfere in your laboratory, yeah. But it's the same. Yeah.
Also, just I have a doubt, like if I have, let's say, 4 telescope, let's say 2 kilometer up, like 2 kilometer by 2 kilometer, and I have a same aperture lens.
Yeah.
So, except the cost of making it, what is the main difference will it come? Like the resolution will be same, but what other major factors will be different than?
Yeah.
Yeah.
I think first, from a technological point of view,
Yeah.
impossible to make
Yeah.
a 2 kilometer
Yeah.
mirror size.
Yeah.
Yeah, yeah, absolutely. So if you could afford, yeah, a 2 kilometer mirror, yeah,
Mhm.
yeah, just construct it. Yeah,
No, no. I mean, like, is there any
I
difference
would be very
between?
happy. Would be very happy. No, in fact, yeah, if you take, yeah, a 2 kilometer mirror, yeah, then you say, well, I could instead use more telescopes. Okay. So in fact, what we are doing is as if we had, yeah, a 2 kilometer mirror, and we set a screen with these holes, yeah, where are the telescope, yeah. Then we reconstruct the images, yeah. Then what we would like to do is to cover the whole mirror, yeah. So we would, of course, transport the mirror elsewhere, you know, put them here, one here. And what you may show that in fact you don't need, yeah, to cover the entire mirror because there is a lot of redundancy, yeah. And so you would just have to find, well, how many locations I would need to set my 4 mirror to have almost complete information. And the number of the posts, yeah, would be limited, yeah. So it will not be a huge number. And people are doing that. Aperture synthesis photometry, well, interferometry is doing that. Yeah. Because remember, during the night, the Earth, yeah, is spinning, and so the star, yeah, sees these telescopes moving and changing baselines and orientation. Yeah, so it's what the people with radio interferometers do. So with 27 antennas, the VLA, yeah, is getting extremely precise images. Yeah.
Any
Yeah.
other questions?
So maybe I can just add that we shall try. Yeah, we do our best to organize a contest in the near future, probably in November, and ask probably a contribution, yeah, connected, related to the liquid mirror telescope. I just said as examples, yeah, well, maybe find another liquid that would be reflective and could be used, yeah, instead, or maybe find cases of microlensing, about which today Yogesh Joshi was speaking, or find, well, doubly image quasars, or find invisible streaks due to space debris, yeah, etc., etc., or bring an original idea, yeah, or not original project that we didn't think about, but related to LMP, yeah. And well, the prize, as we already said, yeah, would be participation to a total solar eclipse, yeah, in Morocco in 2027. And of course, it would be more smaller prizes, yeah. And so we'll organize something and inform all of you, yeah, and we hope that you will participate. So the most important is not to win, yeah, is to participate, as you know. And perhaps now it would be a good time, yeah, to set up, yeah, the liquid mirror scale model, so that people see, what you can do at home, with well, rudimentary equipment. Yeah.
Okay, so the experimental setup is outside. I would first suggest that the students who have come from Nainital go and see it first, because the workshop participants have already seen that, and you'll have to catch the bus at 5:30 p.m. to go back to Nainital. They can take it. They can
5:30.
take it.
Oh yes, 9 minutes. Pas beaucoup, hein?